again to just push on.
And it doesn't matter if we do it many times during the presentation, or you
No.
would rather not?
It's no problem.
No problem. Okay, cool.
Okay, so for the last presentation of this edition, unfortunately the last one already, I have Jose and David with me, and they're going to talk about the geolocation of the GSM mobile devices. So please give me a round of applause.
Hello, good afternoon, everyone. Thank you for coming, and thank you for to the organization too for putting up on this great conference, which we all enjoy a lot. We hope that you find interesting the topic we will be discussing, will be presenting. I'm David, he's Jose, and Tadong is our company. We are a small company based in Spain, and what we are going to be talking about today is how to locate mobile devices, GSM mobile devices, even if they don't want to be found. And what we mean by that, we'll be explaining that in just a second. So geolocation of GSM mobile devices is something that has been considered very important from the very beginning. In the inception of the GSM standard, you can find these location services already defined in the standard. The thought was that it should be very important to be able for the network to find out where exactly a mobile phone was in case of an emergency. So if someone is calling 112, is it 112 here too? The emergency number, like 999 in the States or whatever, or 911. You know what I mean. Well, if someone isn't able to speak, but he's managed to establish the call, then the network should be able to locate it. So from the very beginning, they define those services. And some of them will be network-based, meaning that the network will combine the signals that they are getting from the towers around the victim, around the person, and with that data, estimate the position of the mobile phone, and some of them will be mobile station. MS stands for mobile stations at the mobile device. Mobile station based or assisted, meaning that the network will ask the mobile phone to please tell the network where it is. Because nowadays the mobile phones already have GPS and all the stuff that they know where they are. So the network can ask and the mobile can reply, telling the network I'm at this GPS location. Of course, that's one way to do it, and there's another way, which is installing an application, a spy application if you want, in the mobile phone. So there's this application running in the phone that checks the GPS every now and then from time to time it sends that information someplace else. There are many applications of that kind, and we're not going to be talking about that. Okay? Actually, we're not going to be talking about the services up there either. So what are we going to be talking about? We're going to be talking about how to locate GSM mobile devices, but there was a conversation in a bar, actually over beers, saying, yeah, okay, this is all fine and that, but could we, meaning we, Jose and I, find any mobile phone that we wanted to find, even if we don't have access to the network, so we cannot hack into the network or whatever mobile operator and take that data. And even if the mobile phone has disabled all those location services, so it doesn't answer if you ask him for the position of the GPS position, the mobile phone could have all those services disabled. Like, for example, someone who doesn't want to be found would use a modified terminal that would have those services off. So could we do that? That's what interested us.
In this talk we have two goals. One of them is the first one and the main one, which is to answer the question that David just raised, which is, can we locate a mobile phone, in which conditions and so on. But the other objective that we have is that For us, this has been a research project, and as a research project, we have had some issues, we've taken some decisions, and also we've made quite a lot of errors. And we hope this is of some interest for you because showing the errors that we've had, perhaps others will avoid to make the same mistakes as we did in our project. So these are the two main objectives that we have in the presentation. And from the very beginning of the project, we knew that we had some constraints associated to the problem. Of course, we didn't have access to the mobile network, to the operator. How do you call that? Operator, mobile network? Operator is good, to the network. The mobile station had all its location services disabled. Also, we knew something about the mobile station. We cannot locate any mobile station in the world. First of all, we knew more or less the area where the mobile station was, the neighborhood, around 2, 3, 4 kilometer radius. And we also knew the identity of the mobile station. We knew either the IMA, which, as you know, identifies the mobile equipment, the terminal, or the INSI, which identifies the SIM card. So this is something that we knew in advance. We also assumed that the target was static. It was not on a car or on a train. It was on a room or with something that is walking. And we also wanted to build a solution that was that could be operated as a standalone one. There are other solutions in the market that are based on the deployment of a lot of base stations around there, and they combine the data from all these base stations, and then they give you the position. We didn't want that. We just wanted to make a system that you can put on the car, just drive the car, and locate the target. So in a graphic way, what we wanted was this. We knew that our target was more or less over there, more or less. Then we wanted to go with our car, with our system equipped in there. And then after a while, driving, the system will tell us where the target is as accurately as possible. That was our main objective.
Okay, so we set out in this project and we said, well, let's do an initial design and let's do it right. Let's try to think about the whole life cycle of the software we are going to develop so that we do it right and we don't spend time doing stupid things afterwards, etc. Well, we tried, but you'll see in the rest of the presentation that it wasn't really the case that we managed to do that. The main idea of the system would be a fake base station, a rogue base station, meaning a real GSM base station that we would operate on the car, but it doesn't really belong to any real network. And this base station will be broadcasting signal, announcing itself as one of the real BTSs. Okay, that's the main core of the system. For that, we would use the USRP1, which is a general purpose radio modem device that you can control via software installed in your PC, in your laptop. And then some power devices. We see the power chain here. The top hand side would be the top half would be the transmission path, and the lower half would be the reception path. So we've got our USRP here, and then we've got the power amplifier to amplify the signal being transmitted, our bandpass filter, then duplexer to combine the transmit and receive signals, and that goes to the antenna and out. And then from the mobile phone will come to the antenna, the signal, then duplexer, then bandpass filter, then low noise amplifier, and that back to the USRP one. For the antenna, we decided to use two different types of antenna in different moments. One would be omnidirectional, which radiates all around the car, And then we would use another antenna, a directional antenna, which you can point to some place, and then all the radiation comes and goes from that direction only. And we would use that after we have driven around, and we know more or less where the mobile phone is, we could use that one to get better precision. So if we know that it's in that building, we could point to each of these windows, the windows of, oh, sorry about that. Oh. Almost there, almost there. Yeah, there you go. I'll be careful with this. And then you point that to each of the windows, and then you can determine if it's in that building and if it's not in that window over there, second floor on the right. Okay, that was the idea of using that. We'll cover that in detail. For the software part, we would use OpenBTS, which is a freely available GPL software implementation of a BTS, of a GSM-based station. And we would add some functionality to it, because a normal BTS doesn't need the GPS data acquisitions, and we wanted our BTS to know where it was, so that it could estimate the position of the target. We would add the triangulation of the data received, so that it will estimate that position. That was the main purpose of the system. And then we will need to add some kind of console, so we could operate the system, and we decided to use just simple text-based console, and using the mCarsus library. That was the main setup that we thought we were going to build. The first step after that, after designing the initial design, would be to decide what data we were going to be using to triangulate, to calculate the position of the target. And researching which sources we had available, we knew we had power and we had timing. In our base station, we could measure the power that we were receiving from the target device, from the target mobile phone. We would also be able to know the power that the mobile phone is receiving from us, because the standard implements that. We can ask the mobile phone to report how much power he's seeing from us, and he's obligated, he has to do it, he has to respond with that. So we had those data of power available, and there's also timing. We know when we send signal to the mobile phone, and we know when we receive the response back from the mobile phone, so we could estimate the distance that the signal has traveled. At the beginning, we thought that timing could be prone to errors, because any little mistake, any little error in measuring the time will translate into huge distances, because you're talking about the speed of light. So we thought that maybe that would be not too accurate, and then we would rather use the power data.
So we started to make our program with data based on power measurements, and at first it seemed for us pretty straightforward. I mean, we just needed to take 3 measures of the power perceived from the mobile station from 3 different points, and then just perform a triangulation, which seemed very easy. Mathematics was easy also, and this was our first mistake. It was our first mistake because many reasons. The first one is that, first of all, we have to translate the path loss, which is the signal that is lost when he travels a distance, and we have to translate that into a distance. And for that, there are a lot of mathematical models over there, but the problem with that models is that these models are mainly constructed in an empirical form. So they have been built based on tests and empirical data, and they won't fit well or precisely ever. Never. So even some of these models, like this one, which is widely used, need to use information from the area where you are. So this is quite complicated to make this function in an accurate manner. Another problem that we have with power measurements was that you can use one of these models, you can tune the parameters and adjust the model to the area where you are, but then you take the system, you put it in another place, different place, and then you have to tune it again. If you don't tune it manually, the models won't work. So this is not what we want. We don't want a system that you have to tune manually every time you want to use it. So this is the second problem. And the third problem is that the obstacles in the area have a terrible effect on the data that you have. Here, we had the situation that we were driving with these kind of measures. We were driving, and then the system reported that the target was very near. Then we passed behind a building, and then the system reported that the target was very far. And then again, we went out, and then again very near. It was very annoying and in the practical way impossible to use. So at this point, we just discarded the power measurements as a source of data, and we changed it to another approach.
Right, so we took the wrong approach at the beginning, so let's go for the right approach. We decided then to go back to the timing and see if we could use those measurements. We went through the standard, and we were happy to find a mechanism that is implemented in the standard that's called time in advance. That is a mechanism that allows the BTS to tell any mobile phone to please send your data a little bit later, a little bit after you think you should send it, or a little bit earlier than you think you should send it. And that was to compensate for differences in distance, because any mobile phone located very near the BTS will send the signal and it will arrive right away. But any device being very far will send the signal at the exact point in time that it should, and then that will arrive late to the BTS. So that's implemented in the standard. So we were very happy, because that meant that maybe the BTS knew the distance, so we would just check that distance and off we went. But not really, because this mechanism works with a resolution of one symbol being transmitted on the air, and with the modulation that is used, etc., one symbol translates to 3.69 microseconds, and that translates to 500 meters, more or less. So that meant we could know if the mobile phone was there, plus minus 500 meters, of course. That wasn't really what we're looking for. So we thought we had a huge problem. Fortunately, we weren't discouraged at all yet, and we heard a voice. I know they say when you start hearing voices, you have problems. Don't listen to that. Listen to the voices. Because the voice said, read the source code. And that's what we did. We went back to the source code of the OpenBTS software that runs the BTS, the base station, and we discovered that the timing data is being stored as a float in the C language. That means a huge resolution. That gave us a theoretical resolution of less than 1 meter. And that was good. That was really good. So we were very happy at this point. So we thought that would be a piece of cake, right? We would measure the timing in one point, then move to another with the car, then measure the time, then move to a third point, measure the time, and draw the circles that of the three distance estimations, and they will intersect at some point, and that's it. Really, we thought that would be that easy, right? Well, not really. Problem is that when we started taking those measurements and actually trying to use them, we found out that we were receiving, even having the mobile phone static, in one place, not moving at all, and our BTS static, not moving at all, we will receive the signals like maybe 0.25, between 0.25 or 0.75 symbols before or later. That's huge. That was huge. That's a huge error, but fortunately it's statistical. So it's a random variable that you can calculate the average, and we could use that using statistics. But then there was an additional delay that we didn't expect, and there was this additional delay that was introduced by the mobile phone itself, and it depended on the model of the mobile phone you were using. So an iPhone would introduce whatever time delay extra, fixed, constant, which is nice, but different from what a Nokia would put. And of course, we wanted our system to run against any device without previous knowledge of the brand or model of the device. So that was a huge problem.
And now we had to solve all these problems. And to do that, we had to solve the thing about the variability of the measures. And for that, we were going to use statistics. And also we had to design some algorithms to predict what was the delay introduced by this mobile and other mobile that we didn't know in advance. And at that point, we changed our approach to the project because it was necessary to make a lot of measures, a lot of tests. So we changed our design. Let's go to design and then implement into a way that we just tested something, then implemented another idea that we had, and then tested again. And at this point, the tests were really, really important. And here came another problem. The problem is that in many countries, I think in all European countries, perform this kind of test is highly illegal. I don't know if here in Brussels is also, here in Belgium is also like that. But what we had to do is to choose an area, a country where this is legal. And I can assure you that the country where we did the test allowed us to do that. So please remind that all the tests that we are going to see are legal. Okay, if someone asks you after that, please tell them that. By field testing, what do we mean by field testing? We mean orange field testing, because in that way, in that area, there were a lot of orange trees. So how did we use that orange trees? We used them to hold our mobile phones, our testing mobile phones. We put there in the orange tree, and then we start driving. That was all. And the phone didn't get stolen, so it could work right. And usually there was one of us driving the car, and the other one operating the system. And the one that was not driving was telling the other one, turn left, turn right, put that, go there, or whatever. And what kind of things worked for us when we performed changes in the algorithms? Well, we will show you just a couple of examples, but one of the things that improved the system a lot was changing from taking 3 points and just perform the triangulations, and then the next 3 points and perform the triangulations. We changed that into taking 200 points and then choose the three best and understand best as a criteria that we had to choose also. And once you have chosen the 3 best points, then perform that triangulation. And then again and again and again. And then improve the system a lot. The other thing that worked very well was one thing related with that situation. This is a typical case of intersection that we have to calculate. Any one of here can say where these 3 circles intersect? There is no intersection there. And we had to develop some algorithms to make that in an estimated way. So in this case, for example, the answer was here. And this worked also very well. And with that 2 improvements, we had some quite nice results. But still, we don't have a very precise area where the mobile was. And that is because we hadn't solved still the problem of the delay introduced by the mobile phone. And after solve that, based on some special situations that gave us some clues about what was going on, the results were much better. So these were the main things that we did to solve the problems that David mentioned earlier.
Okay, so at this point, we thought we had success, right? But our system was up and running, and it was calculating the position of the target quite right. So we thought, well, there are a couple of things that we had to do to finish this. And one of the things was impersonating the real network. Up to that point, we had been doing the tests, manually registering the mobile phone to our base station, which was broadcasting a signal in a frequency not used and with a network identifier that was not used in the area. So the mobile phone would connect only to us, and we had that for granted. But then in the real situation, what we wanted the system to do is to drive around and find any device that we wanted that was being served by a real operator, whatever it is. So we need to impersonate the network. And we thought, well, that's really not a problem, because we've done this thousands of times. We've done that in demos many times. And
Always legal.
Always legal. Please remember that. Well, not really. Not really, because the moment we started trying to impersonate the network, what we found that happened was that no mobile phone at all was trying to register with us, not even ours, but no one else's. And it's worse than that. It's not that they weren't trying, they wouldn't even see us in the list of neighbor cells, because every mobile phone keeps a list of the serving cell and then the 6 most powerful cells that it sees around in case it has to change from one to another. Well, we weren't appearing even in that list. So we were below 7th, if something. So we couldn't get the target to connect to us, and without that, our system was useless. Now we remember that we had done that, and honest, we had done that. But then we recall that we had done that using a different BTS, which was a commercial BTS, a small commercial BTS that we had for some of the demos. And then when we reproduced the problem with the other, the impersonating the network with the other BTS, that worked well. So mobile phones were happy with the commercial BTS, but they were not happy with our USRP. Now, why? The first hypothesis was maybe we were not giving it enough power. But that wasn't the explanation, because we tried putting the mobile phone like 1 meter away from our base station, and I guarantee we were frying the terminal. It was getting much more power from us than from the real network. So no, that didn't change anything. That wasn't the problem. Second hypothesis was maybe there's something wrong in the information we are transmitting. Maybe we are transmitting bits that they don't look real to the mobile phone. So, well, to test that, we sniffed the beacon, the broadcast signal of the commercial BTS, which the mobile phones were happy with. And then we hacked the code of our BTS so that it will send exactly the same bit, field by field, exactly the same bits out in the beacon signal. And still, the mobile phones would not connect with us. At that point, we thought this project was dead completely. Happily, however, we kept on thinking, and then we realized that there might be another problem, and that's the precision of the clock. The clock has to be very precise for GSM communication, and we knew that. We had bought the USRP with an improved clock because of that. But maybe it was improved, but it was not improved enough. And sure enough, that was a problem. We measured the frequency we were transmitting at with a spectrum analyzer. We thought we were transmitting at frequency F, and with the spectrum analyzer, we saw that we were transmitting at F plus 900 hertz, which doesn't sound like much when we are transmitting at 900 megahertz, but it is much because the GSM standard allows only for 45 hertz deviation, and we were 900 away. So that's why mobile phones were ignoring us. Workaround for that was hack the code and tell the BTS to tune not frequency F, but frequency F minus 900. So the total effect would be that it would think that it's tuning F minus 900, but it will be tuning F. And that worked really well. And the moment we did that, every mobile phone in the area will try to connect to us. So we were very happy again with this. You see, this project was a very huge series of highs and lows, highs and lows, highs and lows. And you'll see more of those. So we were very happy, because everybody was trying to connect to us. But then we tried to use the system to estimate the position of the target. And that system, the same code that was working perfectly in our test before, was completely not working. We thought it was solved, but it wasn't. They registered, but then the estimated position, instead of converging to a point which was really close to the target, it would diverge. It was completely unstable. And it was the same code that we had been using for months now. So we didn't know what happened. Well, finally, we got down to it and said, well, if the clock is not good enough, let's buy a better clock and put a better clock on it. And that's what we did. And we soldered this one with the clock timer, that's available from Fairwaves, and that really solved the problem.
And at that point, we knew that the system worked. We have almost every problem solved. And we wanted to know what was the range of operation of the system, or in other words, how long do we provide coverage, a false coverage to the targets? And well, testing again to answer that question. And we had good signs, because at first, when we started to test, we configured a completely fake operator, a fake network, with a fake name in a frequency that was not used. And then we manually configured the target to register to that network, and then we start driving and perform the test. And in that way, we reached to almost 2 kilometers of range, which was not bad. So we had good signs. But then came the time to perform the real test. I mean, we had to impersonate a real network. And we configured our system to impersonate a real network. And we started to drive and see at what distance the terminal get registered. And after a while, we discovered that the terminal registered at 15 meters. After all the stuff regarding algorithms, implementation, tests, when we got the terminal registered, then the terminal was there, 15 meters around. No need for algorithms, no need for nothing. We just have discovered where the terminal is. So clearly, this didn't work. And even more discouraging, we knew why was that, because we knew how the terminal choose the cell to have service from. And how is that? Well, the terminal knows the list of neighbor cells because it's given by the serving cell. The terminal, what it does is it performs a list with the 6 cells that it perceives more power from, and then it ranks the cells. If the first one reaches to have more power than the serving cell, then the terminal performs what is called a cell reselection, and then he chooses to go to that cell. So clearly, the problem was that we were not in this list. By the way, this is Samsung Galaxy S2 engineering mode, so you can see that when you want. So what did we do? We just, okay, the problem is we don't have power enough, so let's measure how much power do we need to win the real network. So we went again to that country that everything was legal, and we get very, very far from a real base station, and we measure how much power a normal terminal perceives from that base station. And at that distance, the terminal reported the maximum number that he could report from the real base station. Okay, well, that's a fact. It's tough, but that's a fact. Let's compare it with what the terminals perceive from us. Let's compare it. So we did a graph here. Here you have the power perceived by the terminal. Here you have the distance. That is the line that represents the real network, and these two lines are two terminals reporting what they perceive from us. This distance, that is with the power amplifiers operating, and this distance is not, for us was not, we couldn't win that. And you can't imagine after all the work, how did we feel at that point? We feel discouraged, downhearted. It was, it is very difficult to describe how we felt. So we've made a slide to describe how we felt. It's like if we want to go out with this girl, and then here comes the real operator, which has a very high antenna and a very powerful antenna. And then here you come with your, let's say, normal antenna. Not small, just normal. And then you can imagine which one the girl is going to choose. And from that thought, we had to change our strategy. It was from physical to something more intellectual, you know. And what we did is we invented some magical glasses. And we gave the glasses to her. And then her chose us. Don't worry, we have another cup of glasses for you, and you will see what she is seeing right now. Problem solved. Well, the technical explanation of that is that there is a mechanism called cell reselection offset that is already implemented in GSM, and that is originally designed to perform load balancing between cells. And by that mechanism, you can tell the target, you can tell the mobile station, okay, when you see from me 20 dBs of power, you add up to 60 more. With 60 extra dBs, you have a chance to win the race with the real operator. So this is what we did. We implemented it in OpenBTS 2.6, which was not implemented, and that solved the problem. And this is an example of one registration that we get. The mobile phone was there in that room, and we were there in this, the car was here where the picture was taken, and the mobile phone get registered, so that solved the problem.
Okay, so once again we were very happy because we had the system up and running, it was working, and it was beating the real network, and it was finding the target. Everything was working great, and we had this little tiny thing to do at the end, which was the directional mode. Remember we decided at the beginning that we would have the omnidirectional mode, driving around, getting estimated positions of the target, and then we will have the directional mode. So we would switch to a directional antenna so we can pinpoint the mobile phone exactly where it was in a building, for example. The idea is that simple. We will use power for that. You just point to somewhere else where the target is not, you get low power. If you point to the target, then you get much more power. So we would use a simple bar in the console for that, and that was it. Well, we had those measurements of how much power we're seeing from the network, from the target, and we only had to change the code, to write the code to show that bar in the console. Come on, how hard is that? We thought that would be implemented in like 2 hours. Really, there wasn't that much to it. Yeah. Once again, not quite. Because we implemented it in 2 hours, that was true. But then we went out and tested it. And then what we saw was that we had the bar and we had the power that we were receiving, and we were very close to the target. We were pointing at the target, and then the target was steady. We were steady, but the bar was not. The power we were seeing was oscillating, just going up and down, up and down, up and down. It's true that it was going up and down higher when we were pointing to the device than if you were pointing somewhere else. That would up and down at the lower value at the left. But still, it was very annoying to see that value move around. The cause is something that we actually already knew, and is that GSM, again, has one mechanism to make our life miserable in this project, which was the mechanism that the BTS can use to tell the system, to tell the device, to please lower the power that you are transmitting, because I'm hearing you well, so please save battery. And then if the BTS is not getting enough power, it will tell the device to please send more power, send a higher signal, because I'm not getting you well. Well, that mechanism was actually happening when we were pointing at the device, and it will just go cycling up and down, up and down. Once we realized that the problem was that, well, the solution this time, it was like a couple of hours, really, because actually less than that, because it was hacking the code, finding where that mechanism is implemented in the OpenBTS software, and simply disabling it once we got into directional mode. So once we got into directional mode, that mechanism will be disabled, and the mobile phone will keep on transmitting at a fixed power, and then the bar will just stay at a fixed value.
Well, we're reaching the end of the presentation. We're going to show you the final result of the project. This is not a commercial project, it was just a prototype. As I said before, we were in a place where there are a lot of oranges, and orange boxes work very well for these kind of systems. Air cooling is solved. The fixation of all the parts is very easy with plastic stripes, and you can take these boxes easily and put it on the car. So we made the prototype with two orange boxes, and this is what it looks like inside the car. And for the antenna, finally we had to change the antenna to buy a little better antenna. But the problem with that antenna is that you have to do a hole through the car to install it, and we didn't want to do that. So we had to buy an air freshener box, and we joined the air freshener box with the antenna, and we put some magnets inside, and we painted it on black, and that was the final result of the antenna.
There is actually a side benefit of this system that we realized when we were doing these tests, and we hadn't anticipated. And as when we were doing these tests, with the car driving slow, because we were in a hurry, we were just driving around to find the target, nobody will overtake you. Because they see some funny antenna on top of the car. There's a cable going through the window, and maybe that's the police. So if you want a system so that nobody will overtake you, just build yourself one. Okay, so what precision did we get in the end? Well, we're going to show a couple of examples. This is in an open field environment with all those fields of orange trees. The blue dots here, and going up and right and up, those blue dots represent the path that the car followed. Okay, we were driving the car from here and driving up. Whoops. The mobile phone should be here. It's disappeared from the graph. Sorry about that. And trust me, the mobile phone was here, and we had an icon for there. But in the last save of the graph disappeared. Sorry about that. The phone was actually there, and all those blue dots that you see here, this and this and this, those are the estimated positions that the system was given while driving. So we would start driving down here, and we would get the first dot, and then we will continue and then get a different estimation, and that will converge to more or less this point. But then when we drove past the target, then the precision got really better, much better, and then it jumped to this estimation, and then kept on coming till it was like maybe 20 meters away from where the real target was. And this whole distance here is about 2 kilometers, or 2.5. So it's not bad. So it wasn't bad. And this is an example in an urban environment. Of course, when you're in a city or a town, then it's not the same as an open field environment, because you've got all the buildings and that blocks the signal, so your range is much smaller, it's much lower. But still, you can manage to register the target like 2-3 blocks away. These blue dots, again, is the path that the car followed. And these are the estimated target positions converging to that yellow star there. And actually the mobile phone was there, was in the block across the street. So it wasn't as good as saying that's the block, that's the exact house where the target is, but it was close enough. We knew when we were driving, and we knew we had to get there. And once you are there, well, you know it's around there, you just take the directional antenna, use directional mode, and just point to the 4 buildings you have around, and then you find the exact window where the target phone was seen. Not sound?
I'm sorry. We have some videos here to show to you. This is the console that we had. It's a console based on N courses. Here you have all the messages to the user. You have the IMSI anime here that is not shown because of sanitization. From the first 3 triangulation points, it starts showing one estimated position there and one estimated course to the target. So the target is at that course and at that estimated distance. This is your GPS position. This is a console for an operator, but it is not a console for a driver. After a while trying it with the car driving, we immediately see that it was not operational. So what we did was to develop an iPad console version. Sorry. Okay. The blue dot represents the car, and the red dot represents the estimated target position. This is exactly the same area where we were. It's the same map that we have seen during all the presentations. So it's the same area that we have been talking about during the presentation. If you drive, what we saw is that if you drive around one of the side of the map, then the precision is it's not bad, but it's not very, very good. It's around 60 to 100 meters. But as soon as you pass close the target, because you follow the instructions of the system, then the precision gets very, very accurate, and then it gets stable and it doesn't change a lot. Well, that's the video of the console, and we have another video showing the directional mode. This video was recorded before we solved the directional mode problem. So what you're going to see is that the bar is oscillating a lot. So that's why we had to solve that problem. This is the console. We just switch it to directional mode, and we try to not point into the target at all and then point into the target. And as you can see, the perceived power is increasing more and more. And then we did the other way around. We just pointed to the other way. And you will see that the power perceived is much slower. And with that mode, we were able to identify one target that was in a window, for example. It's very easy because you just point to the window, it's there. It worked quite well. And just the end of this talk is what we would want to do in the future if we have time enough to do it, which is not the case right now, but what we will want to do. We will want to extend the functionality to 3G because it is possible to do it. You have to use another techniques, so you can't use any freeware that is available in the market because there is no freeware that provides a 3G base station, but we would like to do that. We had a couple of ideas about some algorithms that can improve the results. And we also think that it would be nice to have some of the functionality that is in NCORS console to port it to the iPhone console. So that's all, and I think you've enjoyed the talk, and if you have any question, we are happy to answer that.
Can I borrow one of the microphones? Okay, any questions?
Yes, thank you very much for your presentation. Did you try for on USRP2? Because on the USRP1 you have some problem with the clock, and on the new hardware normally it's solved. So did you try with?
At the time of at the beginning of the project, we didn't have an USRP2, so we just used the one that we had. It would have been better to use an USRP2 because it's much more accurate, and the software that you can use is much flexible, but we don't try that.
Just another question, and which kind of data you catch? You base on IMAC for tracking the phone? It's IMAC catching, or?
Yes, the system you configure the system to look for specific devices, and you configure the system to look for a specific IME, how do you pronounce that in English? Whatever, IME, which is the identifier of the device, or IMSI, the identifier of the SIM card that is inside the system. You can use either of those identifiers. So you are getting devices that are trying to register to you, and then the system will just reject whoever is not in that list. And it's not collecting any other information from anyone. It's just concentrated on finding those targets that it has.
As it works is that you have two plain text lists where you put all the IMEIs that you want to find and all the IMCs that you want to find. And the first one that is registered, then he tries to locate that one and forgets all the rest. And if there are other ones, that is just rejected and they get service from the real network. So that's how it works.
Yeah. First of all, I'm very happy that none of you died from cancer yet.
We'll see about that.
Okay. And my question is, how many commercial companies and governments have contacted you to buy your project? And are there any plans in that direction?
We could tell you, but we would have to kill you afterwards. So sorry about that.
How long did it take to build?
How long did it take to build the whole project? Was it?
We had let's say 60% of dedication of David and myself, and for 7 months or so, with all the tests and so on, more or less.
Started to work.
No, from the idea, years. No, from the moment of the work started to the moment that we said that it was already finished.
Does this work worldwide and also in the Middle East? Because if it does, you're rich.
Does it work worldwide? We are not rich. Yes, we are not rich, so maybe that. No. Let's see. Does it work worldwide? The system is using just basic GSM functionality, so it's sticking to the standard. So wherever GSM is implemented in a standard way, the system will work. Now, have we tested the system in many different countries in the world? No, we haven't. We don't want to go to jail, so no, we haven't. Does it work in the Middle East? And if it does, would you be rich with that? Well, if there's an area where there's only 2G coverage, only GSM, maybe there's value there. But if there's also 3G coverage, then the system needs to have 3G added to be of real value.
How noisy is the system? When you say you reject IMSIs and IMEIs that aren't on the list, are you effectively performing a denial of service for every valid subscriber in your area, or are you, do they automatically just go on to their next chosen one of 6?
The question is if we disturb the other users, is that the question?
Yeah. So you, in a 4-kilometer radius, for example, does everyone on orange drop off the network while you're there?
Okay, it's an interesting question, and the way we configure that is as follows. When a user, for example, your mobile phone tries to register with the fake base station, if it is not in the list, he gets rejected. But the key here is what is the code that we give to them by rejecting cause. So the code that we give to the mobile phone is rejected because you are not allowed to register in this location area. And we configure the location area absolutely different from the real network. So the effect of that is that one mobile phone will only try once to register against our fake base station. So we disturb any other users very, very, very little.
Hello. You've said at the end of the presentation that you foresee to, if you have time, to work on a version that works with 3G. But a difference in 3G is that the network has to authenticate to the mobile phone to establish the connection. Is this an obstacle that will prevent any attempt to port that project to 3G, or is it at different layers? And when you say the mobile attached to your base station, it's at a very low layer.
That's a very good question. In 3G, the authentication is different, is finally bidirectional. So the mobile phone verifies the identity of the network before actually registering and using the service of the network. But the question is, can we still do the same that we are doing here in 3G? And the answer is yes. And the answer is in what you said, is using lower levels. So before you get to actually complete the authentication, there's a lot happening on the air. So using that, it is possible. It wouldn't be exactly the same as we have done here because it was easier in 2G, but it is possible, yes.
Time for one more question.
So you have equipment, you're able to send and to receive. Just a theoretical question, how difficult would it be to modify the system to listen to the conversation going around?
That was not the aim of the project, the fact is that this is already solved. For example, if you configure OpenBTS, which is an open project that you can download and install it on a USRP, you can do that. For example, you can force any terminal to register to your base station and then route the call. For example, using voice over IP, and then you are in the middle of the conversation, you can listen to it. So this is already solved, so this can be done.
So the providers, they don't encode the signal, they don't provide some kind of a security that somebody that has equipment can listen?
Yeah, well, the protocol provides security on GSM, a security that is broken. But even you don't need to break the security because when the terminal registers with a fake base station, the base station tells the terminal, you are going to use algorithm A50 to encrypt. You know what A50 means? no encryption. And by specification of the protocol, the terminal is obliged to get with it. So yeah, there is security in the protocol, but there is also a way to break the security even in the protocol. Said that, the A51, which is the encryption algorithm, has been also broken. So we're talking about 2G.
Okay, so with this we can round up this presentation. Please give them a round of applause.
Okay. Now, before really rounding it up, we had Enviso, one of the sponsors, has run a challenge on their booth, and they wanted to announce the winners of those. So maybe you can come here.
Okay, I will just keep this very short because we don't want to take too much of your time. So when we had our booth here, I wanted to put an open bar without any challenges because I don't think that's what you guys want. But my colleague disagreed, so in the end we had to do challenges. I hope most of you enjoyed them a bit. We tried to make them as fun as possible. We got quite some participation, so thanks a lot for that. And as you all know, we promised some nice prizes. So let me just take my list of people who have actually won the game and we'll get you on the stage for a second, or at least the people that we know are still here. Let me check that. 1 second. This is not manipulated, it's all... So, for our technical security challenge, we had 4 guys in the top 4. The first one is number 4 is Fernando Roja. I don't know, could you please join us? Then we have one of the BruCON volunteers, I think, Ivan Janssens. Are you around? Yeah, just join us all for a second. Then we have, then we have Sean de Regge. Is he? And number 1, but he left us already, is Jerome Kleinen. He already got his prize. So we promised you guys a Raspberry Pi. So Dan, could you... Yeah, you will have to share it, so... The budget didn't allow anything else. Our booth was already too big, so... No, that's just kidding. So here we have... I'll just...
I'm the assistant.
So have fun with that. We also, of course, had another challenge, which my other colleague, Kurt, here will explain. Go ahead.
Yeah, so very short, there was a box with locks in it, and you had to basically guess the number of locks. Actually, right answer was 71, so the person who got closest to it was Senne van Vinkenrooyen. So normally he got an Enviso quick scan, but that was for a professional participant, so we also have a Raspberry Pi for him. So I don't know whether Senne is still here, but he can join the stage. I guess he's already off. Yeah, okay, so we'll contact him by email, send it to him. And then the closest professional one to the lock answer was Fabien Talgot. So we'll contact him actually for the free Enviso quick scan. What? Fabien Talgot, is he still here? Okay, but we contact him again. So yeah, thank you for attending. I'll give it back to Seba.
Okay. So a couple of last words. I would really also indeed like to thank all the sponsors for making this happening. And I really want a big applause for our volunteers who helped us out really big time. So, and thank you for coming. We are going to do this again next year in this same building, and the dates are 25 and 26th of September, and hope to see you then. Safe travels home.